Greetings. In today's session, we will discuss about principle of minimum potential energy. As we are aware that the total potential energy possessed by any system is summative value of strain energy possessed by the system plus the potential energy potential energy of the external forces acting on it. If we are taking the partial component parts, incremental part of this one, we can say di by pi is equals to di by u plus di by wp, where the u is nothing but the strain energy and wp is nothing but the potential energy of an external forces. So here we are going to consider incremental values for it. So incremental values will be also a summative value of increments in strain energy and increments in potential energy of external force. We have also gone through the relationship of potential energy with reference to the applied forces. There are two types of forces applied on a structure. They are the external force and the body force. When we say the work done by both the forces are being accounted, we say the total potential energy of external force will be equals to the product of the force multiplied by the displacement in respective direction over the volume. So in case of body forces, it will be product xb into u plus yb into v plus zb into w, whereas in case of surface forces, we are going to say it is a product of the surface force multiplied by the displacement component in respective direction over the entire surface, which this value is generally equal and opposite to the virtual work done by the external forces. So if I apply here virtual work principle, the virtual work principle, we see that there is an external work done by the applied forces. We say this external work done is nearly equal in magnitude with reference to the potential energy of external forces. So we can say wp is equals to minus we. So again we can say increment di by wp is equals to di by we. So incremental in the your potential energy will be equals to the incremental work done by the external force in case of virtual work done. That's why di by pi is equals to di by u minus di by we. But from the principle of virtual work done by external forces, the strain energy equals to the work done by the external forces. So here the statement says that if I am going to see the principle of virtual work done, then we can say the external forces produce strain energy which equals to the work done by the external forces on it. So that's why we can say di by u is equals to incremental value in strain energy will be equals to exactly equal to the incremental work done in case of virtual work principle. That's why dou u can be equated as a di by u, it can be equated as a di by we. If we substitute this value here, so here w di by u will be replaced by di by we. That's why di by u here it will become di by we minus di by we is the resultant is 0. Means what the product is here 0. The incremental strain, the potential energy will be equals to 0. It means that it is having a minimum value. Okay, so for a deformable body is in equilibrium when the total potential energy is having a stationary values. By taking second variance of the potential energy, it has been proved by researchers that the value is positive definite. Okay, here if I take the second variance of this particular relationship, I am going to get a value which are positive, and hence we can conclude that the value of the total potential energy is stationary, corresponds to minimum value. Hence we have the principle of minimum potential energy in a solid mechanics, which may be stated as of all the possible displacement configuration a body can assume which satisfy the compatibility and boundary condition, the configuration satisfy the equilibrium makes the potential energy assume a minimum value. Means what, for all the given configuration, displacement configuration and compatibility condition or boundary condition, if I am going to satisfy the equilibrium, it generally makes the potential energy to be minimum value. This is also called as a this principle is also called as a variation principle in case of solid mechanics. Let us start to prove with some standard relationship. Let us go with the reference to the principle of minimum potential energy and equilibrium equation in a spring system. This we say it is ideal elastic system, and the behavior of this ideal elastic system will relate to a relation which will state that minimum potential energy and equilibrium, they are going to balance each other or they are going to merge nearly the same value. Let us consider a system of springs are being there in a series. The first spring is having a spring constant as a k1, the second spring has a spring constant k2, and the third spring is having a spring constant end of spring A1 having the stiffness spring constant K1 is one end is fixed and the other end is joined at a node 1. This node 1 is common to the spring 1 and 2, and similarly node 2 is common between spring 2 and 3, and the node 3 is at a free end. Let us assume that at these respective nodes there are applied forces F1, F2, F3. Now we will say these applied forces will do some work and there will be certain strain energy develop in this particular spring. We will try to get minimum potential relationship with reference to the equilibrium of the forces which are applied at particular nodes. So for that, let us consider the displacement at nodes be U1, U2, U3, node 1 U1, node 2 U2, and node 3 U3 respectively. Similarly, the extension of the springs at 1, 2, 3 will be equals to, now here the spring may have extension, let us say diba 1. The diba 1 will be equals to U1. Here in the case of the node 2, there will be the extension for both the parts. Here it will be resultant, what we can say, if I go for with reference to here first node here at this one first node here, so here this node is having inextensible value. That's why at node 1 it will have only diba 1 equals to U1, diba 2 will be equals to U2 minus U1, and diba 3 will be equals to U3 minus U1. Now let us go towards the equilibrium equation to know about what type of the forces is going to attracted at that particular node. So here F1 is the force applied on the node, and here K1 delta 1 is nothing but the force which is developed due to extension in spring 1 with spring constant K1, and say similarly we will have one more opposing reactive forces develop in the spring 2 with a spring constant K2 into diba 2. Similarly, if I have equilibrium equation for the node 2, I will get the same assembly K2 delta 2. This is the force attracted by the spring spring with a spring constant K2, and K3 delta 3, it is the force attracted by the spring with spring constant K3. And similarly at the node 3 we will have one force component acting here K3 delta 3, and the external force acting here is F3. Now let us go in depth with reference to the calculation related to equilibrium equation. Now I am going to write the equilibrium equation with reference to the figure which we have just discussed. At node 1 it will be K1 delta 1, K1 diba 1, here diba 1 will have extension will be in negative sign because it's going to be in opposite direction, plus K2 diba 2 plus F1. So these are going to be towards right hand side, these are going to be towards left hand side. Based on the sign convention, I can write the equation this, the forces along x-axis along a particular direction should be equals to 0. Similarly, I will write for the node 2, at node 2 two forces are going to act K2 diba 2 plus K3 diba 3 plus F2. The K2 diba 2 will have negative value because it's going to act in towards the left hand side, and towards the right hand side K3 diba 3 is there, plus F2 is going to be towards right hand side. Likewise, I will write equilibrium equation for 1, 2 and 3. At third node we will get an equilibrium equation minus K3 diba 3 plus F3 is equals to 0. Now I will put individual the value of the diba 1, diba 2, diba 3 in terms of displacement component in respective direction. So here we have considered for node 1 it will be U1, node 2 it will be U2, and node 3 it will be U3, the total displacement at that particular node. That's why we'll have the equation, rewrite the equation as K1 U1 plus K2, here diba 2 is nothing but U2 minus U1, we call as a resultant displacement here, plus F1. So similarly we can write for the second equation, substitute U2 diba 2 value I am going to substitute here, it will be U2 minus U1 plus U3 minus U2 plus F2. Similarly for the third equation, U3 minus U2, that is a diba 3 value, plus F3 equals to 0. If we rearrange this one by taking constant on one side and the displacement and spring constant on other side, the forces if I take on the left hand side and the reactive forces on one side, we get a equation here K1 plus K2 U1 into U1 minus K2 into U2 is equals to F1. Similarly, second equation we can obtain, third equation we can obtain. Now if I write in a matrix format, this we can write it in matrix. I am going to take coefficient spring constant because they are the constants value, and U1 and U2 and U3 we will call it as a displacement tensor, and here F1, F2, F3 we will call as a force tensor. So we can represent this value in terms of matrix relationships. So we will get the matrix K1 plus K2 minus K2 0 minus K2 K2 plus K3 minus K3 0 K minus K3 and K3. Then we'll now after equilibrium we have got a relationship in a matrix format like this. Now we'll move towards with reference to the potential energy theorem. So we know that total potential energy in the system is pi equals to U plus WP, where U is nothing but the strain energy. If I count for the strain energy of the spring, we have a relation 1/2 of the spring constant multiplied by the displacement here. So here 1/2 of K1 into di by 1 whole square will be for the first spring. For the second spring, we'll have 1/2 K2 di by 2 whole square, plus for the third spring, we'll have 1/2 of K3 into di by 3 whole square minus F1 U1 minus F2 U2 minus F3 U3. If I substitute the respective values of di by 1, di by 2, di by 3 in this equation, I will get 1/2 of K1 into U1 whole square plus 1/2 of K2 in bracket U2 minus U1. It should be here U1 whole square plus 1/2 of K3 into U3 minus U2 whole square minus F1 into U1 plus F2 into U2 into F3 into U3. These are the potential energy which is being acted due to applied forces here. If I say the values to be merged to a minimum one, so I will say the partial derivative of this total energy with reference to the unknown displacement component should yield to 0. So di by pi upon di by U1 according to minimum potential energy theorem, I can say it should be equals to 0. That's why I will have the partial derivative of this individual equation with reference to U1. So we will get K1 U1 plus K2 U2 minus U1 in bracket minus 1. Here 2 will come downward, 1/2 of 2 in 2 by 2 they get cancelled. Here if I say 1 upon 2, so here square derivative 2 will get 2 by 2 get cancelled. Here K into U2 minus U2 will remain in the bracket, multiply by minus 1 because I am going to consider the derivative with reference to 1. Here by mistake I have put here 2, it should be considered as a 1. So here it will be minus 1 minus of F1 equals to 0. If I rearrange this equation, I will get the relation K1 plus K2 into U1 minus K2 into U2 is equals to F1. Similarly, I will go for the second part because of one more unknown displacement component we have U2. I will derivate the total energy equation with reference to the your displacement component U2. Then we get a relation K2 into U2 minus U1 plus K3 into U2 minus U2 into minus 1 here. So here again we will see the equation here. I am going to differentiate with reference to U2. So what will happen here? These two will get cancelled. Only what remains U2 minus U1 here. But we are going to differentiate with U2. U2 will yield in a positive value. That's why we will consider here as a 1. In the second case, it will U2 will have the negative component because square will get cancelled, and in bracket this derivative of U2 will be yield to minus 1. If I rearrange the equation, I will get a relation likewise minus K2 U1 plus K2 plus K3. It should be here K3 into U2 minus K2 K3 U3 is equals to F2. Now here dou pi by dou U3. I am going to differentiate with reference to third component, displacement component. That's why I will get K3 in bracket U3 minus U2 minus of F3 equals to 0. So we'll get the relation minus K3 into U3 plus K3 into U3 equals to F3. I will put this all relation yielding value in matrix forward. Again I will get the matrix will have K1 plus K2 minus of K2 equals to 0. K1 minus K2 0 minus K2 in bracket K2 plus K3 minus K3 0 minus K3 K3. This will be said to be a constant matrix of a spring constants, and here we will get the displacement tensor, and here we will get the your force tensor. If we compare with reference to previous equation, they are near they are likely same. Okay, both approaches yield exactly the same. Thus we can say the potential energy should have extreme value, that is a minimum, which leads to the equation of equilibriums. Okay, so here we can make a statement that either we can go with a equilibrium states, or we can say potential energy is minimum only when the equilibrium stage is arrived. Now we'll move towards the part of numerical. Principle of minimum potential energy and equilibrium system, spring system numerical. Here in this numerical, a system of springs has been given, which are being connected at 4 nodes 1, 2, 3, 4 with different values of your spring constant K1, K2, K2, K3. 2 springs are in parallel, and these are in series system. So here the values of K1, K2, K3 is given to us. K1 is 40 Newton per